Hey everybody, this video is about linear or not, and this is how we're going to decide if tables are in fact linear, and then if they are, how are we going to link this concept with slope, which is what the previous videos were about. So we actually already talked about how to tell if a table is linear. You're looking for that pattern. So one more time, to be linear, for every constant change in x, there must be a constant change in y. Okay? And this, again, is to tell if something is linear. Okay? So to be linear, that's what you're looking for. So let's see if we can spot the pattern. Otherwise, we're going to do some calculations. So here we have our x's increasing by ones every time. And what I like to do is show the pattern on the side. So all of these changes are ones. My output is actually changing by the same amount of 1.5, but you might not notice this because we don't work with decimals as often as we work with whole numbers. So there's got to be a way for us to figure this out using the concept of slope. Well, otherwise, another way to phrase this, for every constant change in x, there must be a constant change in y, is that there must be a constant rate of change, which is another phrase for slope. And we know that slope is calculated by the change in y over the change in x. So let's see if we can do this calculation all the way down the table and see if it comes out the same. So these are two ordered pairs. I'm going to take the first two ordered pairs, -3, -7.5, and -2, -6. I'm going to call this one x1, y1, and I'm going to call this one x2, y2. If I calculate slope, and do my substitution, this is going to be -6 minus -7.5 over -2 minus -3. We know that minus minus becomes plus, so this turns into addition, and this turns into addition. And then when I do these calculations, I'm going to get 1.5 over 1, or just 1.5. Make sure that's true all the way down. So my next two ordered pairs are -1, -4.5, and -2, -6. Do the same thing. Call one of them x1, y1, call the other one x2, y2, and see if their slopes are the same. So I'm not going to keep writing the slope formula anymore. I'm just going to jump right in. So this is going to be -6 minus -4.5 over -2 minus -1. If I do the math, minus minus becomes plus. This is going to be -1.5 over -1. But a negative divided by a negative is a positive. And so, yeah, I do still get 1.5. Keep checking it out all the way down. So the next set of ordered pairs would be 0, -3, and -1, -4.5. Calculate the slope again. Slope is going to be -4.5 minus -3 over -1 minus 0. When I do the math, I get -1.5 over -1. Look at that, 1.5. So you do want to make sure that it's true all the way down. So you would keep going, okay, just to make sure. But we can see that this change is always going to be 1.5 change in y for every 1 change in x, the same way that we described it earlier. All right, let's try another one. Here's another table. With x and f of x. I've got 0, 2, 5, 6.5. And I have 100,000, 70,000, 25,000, and 2,500. And I want to know if this is linear. Okay? I can see that if I do these changes along the side, I have a change of 2, I have a change of 3, I have a change of 1.5. Looks like I'm going to have a problem here because those x values are not changing the same amount. Same thing over here. This change is losing 30,000. I'm losing 45,000. I'm losing 22,500. But remember, that's not going to necessarily be the indicator. I need to see if this relationship stays the same. So I'm going to go back and I'm going to calculate the slopes. I want to see, so again, slope formula is the change in y over the change in x. I want to see what I get when I use the formula. So this is going to be 70,000 minus 100,000 over 2 minus 0. This is going to be negative 30,000 over 2. And when I calculate that, I get negative 15,000 over 1, or just negative 15,000. Let's keep going. Calculate the next slope. If you notice, this is the change that we've already done in the table. Negative 30,000 is this change. And then the 2 was this change. So if you've already done that in your head, you don't have to go and substitute back into the formula. We can just use it directly from our sides of the table. My next rate of change is going to be, if you were going to plug in 25,000 minus 70,000 over 5 minus 2. But again, you might have already done the math. It's just that negative 45,000 over 3. But look at that. What is negative 45,000 divided by 3? This simplifies, again, to negative 15,000 over 1, or just negative 15,000. So far, this is looking pretty promising. Let's try the next one. I'm not going to go and plug it all in again. I'm just going to use these numbers. It would be negative 22,500 divided by 1.5. The change in y, the change in output, divided by the change in x, or the change in input. Guess what? When you calculate this, you're also going to get negative 15,000. So even though it didn't look linear in the table necessarily, this is in fact linear. And not only is it linear, we also figured out by default that the slope was negative 15,000. Now let's try to bring this all together, because I know it's going to be hard for some of you to see how this comes out to be something that's linear. Remember that we're looking for that pattern. For every change in x, there should be a constant change in y. My first value was 0, 100,000. According to the slope that I just calculated, which remember you can always put over 1, so this way it looks like rise over run, I'm supposed to lose 15,000 every time my x changes by 1. So that means that when x is 1, this is a change in 1, I'm supposed to lose 15,000. And that's going to put me at 85,000. When I go to 2, which is another change of 1, I'm supposed to lose another 15,000. Well, what's that going to take me to? That's going to take me to 70,000. So all I'm really doing is I'm filling in the missing values from the table. I didn't see the point 185,000. But now that I know that there is a constant slope, I can put it in. Then you can continue. When x is 3, I'm supposed to lose another 15,000. And so this would wind up being 55,000. When x is 4, I'm supposed to lose another 15,000. So that would put me at 40,000. And when x is 5, I'm supposed to lose another 15,000. And that puts me at 25,000. Did that fill in the missing gaps that were in the original table? Yeah, it did, because I got the next ordered pair of 5, 25,000. So all this is doing is showing that even though the original pattern might not have looked constant, when you break it down to every one, it is really constant. And so you have to look at this relationship, the change in output divided by the change in input. This lets you get ready for the game Linear or Not that we're going to be playing. So this is the type of thing you're going to be asked to do. You're going to be given tables like this, and you're going to have to decide if you do in fact have a line or not. The slope. Let's look at one really quick so that you can see the difference. So here's one last example. Let's use 7 with outputs of 39. Well, this side is looking pretty good. This side is all changing by ones. But this side is changing by a variety of different amounts. This changed by 10. This changed by 12. And I could actually even stop there. 10 to 1 is not the same thing as 12 to 1. So this does not have the same change. So this is not linear because there is not a constant rate of change. And we can even say 10 to 1 is not the same as 12 to 1. Okay. The last thing I want to leave you with in this part of the video is this is not rate as in the rate that we talked about for exponentials. This goes together as one phrase, rate of change, because the change is that subtraction that we talked about in the previous video. So we're not talking about rate as a percentage here, okay? This is not like exponentials. We're talking about rate of change as in the change in y to the change in x. So I want to show you what I have ready for you guys. In Blackboard, put in a game that I want you guys to play, and hopefully we'll be playing it live on Friday, but I left it up for you right now. So this is Blackboard, and underneath content, you have the linear functions module, and this is all the things related to linear functions. And all the way on the bottom, I put the linear or not game. It's a Kahoot game. So if you open it, it's going to take you to Kahoot, which is a challenge that I created for you. So you'll see that when you click on that link, it's going to load a game. All you have to do is give yourself a name. Okay, so I'll just put, you don't have to give yourself your full name. Okay, I don't need to know who did it or not. And then it starts the game. And it's asking you, is the table linear? And not only do you have to figure out if it's linear, you have to also decide what the slope is. Okay? You have 60 seconds for each table, and then you can guess. And you can play as many times as you want. Just give yourself a name. So I hope this video made sense. I hope it flowed well from the previous videos. This is what I'm hoping to do on Friday of this week. You can look at how it coincides with the calendar. And I hope you guys have a great day.